Hi, my name is Yufeng. In the following, I will present IMAvatar, a method for learning implicit morphable head avatars from videos. The input to our method is a monocular video sequence, along with the corresponding foreground masks and the tracked 3DMM parameters. And our goal is to build head avatars, which models geometry and texture details, and also can extrapolate to novel expressions unseen from the training distribution. Animatable avatars are traditionally modeled by 3D morphable models. These methods offer explicit geometry and fine-grained generalizable expression control, but they cannot easily model photorealistic appearances or detailed geometry. Non-skin regions such as hair and teeth are also generally not included. Recently, neural implicit representations have emerged as a powerful tool to represent photorealistic facial avatars. However, they fail to generalize to novel poses unseen from the training distribution. Furthermore, modeling the deforming facial geometry is also difficult. So how can we introduce 3DMM level controllability into photorealistic neural implicit avatars? First, let's take a closer look at how 3DMMs perform mesh morphing. In our case, we use Flame. The Flame model deforms the canonical mesh by adding the expression and pose correctives, and then it performs linear blend skinning to obtain the final mesh. Since the blend shapes and skinning weights are all pose and expression independent, Flame can extrapolate by formulation. We represent the blend shapes and skinning weights as continuous fields and formulate our deformation in a similar way to Flame via implicit morphing. Given the target pose and expression parameters, we can calculate the deformed location for each canonical point. In summary, IMAvatar is parameterized via the canonical texture, geometry, and deformation fields. In the blue box, we show the learned skinning weight and the learned blend shape for an example expression. Next, let's look into how to learn IMAvatars from posed images. We first perform remarching in the deformed space. Then, for each deformed point, we need to locate its correspondence in the canonical space where the geometry field is defined. However, the location of the canonical point xi sub c is only implicitly defined. Therefore, we leverage correspondence search to find the canonical location xi sub c in an iterative manner. We can then determine the occupancy value of the sampled points by querying the geometry network and locate the nearest surface intersection for each pixel. Once the canonical surface point x sub c is located, we can query the texture network to obtain the RGB value for the pixel. But first, we must derive the analytical gradient for x sub c in order to avoid backpropagation through the iterative process. We observe that the location of the ray surface intersection satisfies two constraints. First, the canonical point must be on the surface, and second, the deformed point must project to the pixel location. With implicit differentiation, we can calculate the gradient of the canonical location x sub c without backpropagating through the iterative process. IMAvatars are learned end-to-end from a monocular video using image reconstruction loss and a foreground mask loss. Optionally, when the expression diversity is limited in the training data, we can leverage prior knowledge from Flame by supervising the predicted blend shapes and weights. Now let's see some results. First, we show our results on the MakeHuman synthetic dataset. IMAvatar can learn detailed geometry and texture from monocular video and generalize to novel poses out of the training distribution. IMAvatar can also learn from real sequences and can be correctly animated using unseen expression sequences. Note that the details are not only in the texture space, but also in the deforming facial geometry. Here, we show extreme extrapolation of individual expressions. We control the first expression parameter of Flame, giving us a smile. We can also move lips from one side to another and raise eyebrows. Thank you.